April 1946. A French farmer guides his plow through a field outside Caen. The blade strikes something metallic buried 18 inches below the surface. There is a muffled crack, then a cylinder launches upward to waist height. The explosion kills him instantly and blinds his son standing 20 meters away. The mine that ended his life had been dormant in the soil for 2 years. It was designed by German engineers in 1935. It would kill more people after the war ended than it did during active combat. The S-mine, designated shrapnel mine by Wehrmacht ordnance departments and called Bouncing Betty by Allied forces, was engineered to maximize casualties against infantry advances. Unlike conventional anti-personnel mines that detonated where they lay, the S-mine used a two-stage firing mechanism. The initial trigger launched the main charge into the air before detonation. The blast occurred at approximately 1 meter above ground level, projecting steel fragments horizontally across a kill radius that made conventional mines obsolete. The problem facing German military planners in the early 1930s was geometric. Traditional anti-personnel mines buried in soil directed most of their explosive force downward into the earth. A soldier stepping directly on a conventional mine would likely be killed or maimed, but soldiers 5 meters away often escaped with minor injuries or none at all. The ground absorbed energy. Shrapnel was deflected upward at steep angles, passing over the heads of nearby infantry. To cover an area effectively required dense mine placement, which was resource-intensive and time-consuming. German engineers needed a mine that could deny larger areas with fewer units, and they needed it to function reliably in the soil conditions of Eastern Europe, where much of the coming war would be fought. The solution emerged from the Metallwarenfabrik Treuenwritzen facility in Brandenburg. The S-mine consisted of a cylindrical steel canister, approximately 4 inches in diameter and 5 inches tall, containing 360 grams of TNT surrounded by steel balls or scrap metal fragments. The canister sat inside an outer casing. 3 prongs extended from the top of the outer casing, protruding slightly above ground level. When pressure was applied to any prong, or when a tripwire connected to the prongs was pulled, a small propellant charge at the base of the canister ignited. This charge, containing approximately 5 grams of black powder, launched the inner canister vertically out of the casing. A delay fuse ignited during the launch, timed to detonate the main charge after 0.4 seconds. At the propellant velocity achieved, 0.4 seconds meant the canister reached between 0.9 and 1.2 meters in altitude before detonating. The explosions sent fragments outward in all directions at velocities exceeding 1,200 meters per second. The lethal radius extended to approximately 15 meters. The casualty radius reached 30 meters. Fragments retained enough energy to cause injury at 50 meters under optimal conditions. The S-mine entered production in 1935. Initial versions, designated S-mine 35, were deployed during the Spanish Civil War in limited numbers. German forces used them primarily for perimeter defense and to protect fixed positions. Combat reports indicated effectiveness exceeded projections. A single S-mine triggered in an advancing infantry section typically produced between 3 and 7 casualties. Conventional mines averaged less than 2. The psychological effect was substantial. Soldiers who witnessed an S-mine detonation reported extreme reluctance to advance through suspected minefields, even under orders. Production accelerated in 1939. The improved S-mine 44 incorporated a simplified fusing mechanism and reduced the steel casing thickness to conserve materials. Approximately 1.93 million S-mines were manufactured between 1935 and 1945. German forces deployed them extensively across every theater. In North Africa, Rommel's engineers laid S-mine fields in front of defensive positions at El Alamein. British infantry advancing at night triggered multiple mines. After-action reports from the 2nd New Zealand Division documented that casualties from mines outnumbered casualties from small arms fire during specific assaults. In the Soviet Union, German forces used S-mines to defend supply routes and communication lines. Soviet infantry tactics, which emphasized mass assault, proved particularly vulnerable. A single minefield could inflict dozens of casualties on an advancing rifle company before conventional defenses engaged. The S-mine's most dangerous characteristic was not its kill radius. It was the difficulty of clearing it safely. Conventional anti-tank mines could be disarmed by carefully removing the pressure fuse. Anti-personnel mines could sometimes be deactivated by cutting visible tripwires. The S-mine incorporated anti-handling devices. Many units included a secondary fuse at the base of the outer casing. Any attempt to lift or disturb the mine triggered detonation. Even when engineers successfully identified and avoided anti-handling mechanisms, the design meant that any disturbance of the prongs could launch the canister. Engineers attempting to disarm S-mines worked knowing that a single mistake would send the main charge directly into their torso before detonation. British Royal Engineer casualty rates during mine-clearing operations in Normandy were among the highest of any specialized role. American forces developed specific procedures for S-mine clearance. Engineers used long poles to probe soil at shallow angles, attempting to locate mines without applying vertical pressure to the prongs. Once located, the standard procedure was not to disarm the mine, but to destroy it in place using explosive charges. This was safer for the engineer, but time-consuming. A single minefield could take days to clear. German forces understood this. They laid S-mines in mixed patterns with anti-tank mines, forcing engineers to approach every metallic signature as potentially lethal regardless of size. Soviet mine-clearing methods were more direct. Penal battalions were sometimes ordered to advance across suspected minefields ahead of assault troops. The mines detonated, clearing paths and revealing minefield boundaries. Casualty rates among these units approached 100% in some documented cases. The Soviets also employed trained dogs carrying explosive charges, though this program was largely ineffective and abandoned by 1943. By May 1945, an estimated 300,000 S-mines remained buried in French soil alone. Millions more lay in fields, forests, and roadsides across Belgium, the Netherlands, Poland, and Germany itself. Wehrmacht engineers had laid mines as defensive positions collapsed, often without recording locations. Maps were lost, destroyed, or never created. The mines did not degrade quickly. The steel casings resisted corrosion. The mechanisms remained functional indefinitely in dry soil conditions. The TNT filling was chemically stable. A mine laid in 1943 was equally lethal in 1950. French authorities organized mine clearance operations beginning in 1945. The work proceeded slowly. Engineers used the same methods developed during combat, probing and marking. Civilian casualties mounted, farmers plowing fields, children playing in the woods, construction workers excavating foundations. The mines made no distinction between Wehrmacht infantry and French civilians. Between 1945 and 1950, S-mines killed an estimated 2,500 French civilians. In Belgium, the number exceeded 1,800. In the Netherlands, approximately 1,200. These figures do not include Germany itself, where accurate records were not maintained during the immediate post-war period, but estimates suggest casualties in the thousands. The casualty profile differed from combat. During the war, S-mines killed primarily military-aged males wearing uniforms and carrying weapons. After the war, victims included children, elderly farmers, and women. The injuries were identical. Fragments traveling at supersonic velocity do not distinguish between a Wehrmacht soldier and a 10-year-old French boy. The blast pressure that ruptures organs functions the same regardless of who stands in the kill radius. Mine clearance continued through the 1950s. By 1960, French authorities declared most agricultural areas clear, though warnings remained posted in forests and along former defensive lines. Occasional discoveries continued into the 1970s. The last confirmed S-mine casualty in France occurred in 1983, when a hiker in the Ardennes triggered a mine that had been dormant for 38 years. He survived with severe leg injuries. The mine functioned exactly as designed. Modern detection equipment eventually made clearance more effective. Metal detectors could identify buried casings, ground-penetrating radar could map suspected minefields.
But these technologies arrived decades after the mines were laid. The gap between deployment and clearance was measured in generations. The German engineers who designed the S-mine in 1935 built a weapon that remained lethal for half a century. They created something that would kill farmers and children in fields that had never seen combat, in a war that those victims had not fought, triggered by footsteps that were not advancing against any enemy. The last significant S-mine clearance operation in Western Europe concluded in 1998. Engineers removed over 400 previously unmapped mines from a forest near the former Siegfried Line. Every mine tested after removal functioned correctly when detonated in controlled conditions. 63 years after manufacture, the mechanisms still worked, the propellant charges still launched, the delay fuses still fired, the fragments still killed at 15 meters.